Assalamualaikum, my dear subscribers and new viewers. In today's episode, I will be presenting two problems involving capillary action, which is the ability of a liquid to flow through narrow spaces without external forces such as gravity. So to understand more, just stick around, watch and learn. Why is capillary action important to living things? Capillary action allows plants to get water throughout their tissues, which enables them to survive. Since herbivores cannot live without plants and carnivores cannot live without herbivores, capillary action helps sustain life on Earth. Question number 1. Water rises in a glass capillary tube to a height of 8.4 centimeters. What is the diameter of the capillary tube? Let the surface tension capital T of pure water be equal to 0.072 kilogram per second squared and its density equal to 1.00 times 10 to the third kilogram per meter cube, and the angle of contact theta equals 0 degree. Question number 2. At 25 degrees Celsius, how low will mercury drop in a glass capillary tube with an inner diameter of 0.63 millimeters? Use the surface tension of pure liquid mercury, capital T, equal to 0.458 kilogram per second squared, and the density of mercury equal to 1.36 times 10 to the fourth kilogram per meter cube, and the angle of contact theta equals 135 degrees. What is a capillary action? It is the flow of liquid within a porous material due to the attraction of the liquid molecules to the surface of the material and to the other liquid molecules. When a glass tube is immersed in a container of pure water, a column of the water flows through and rises in the tube. The adhesive forces of water with the walls of the capillary tube are stronger than its cohesive forces, causing it to rise. On the other hand, the cohesive forces in liquid mercury are stronger than its adhesive forces, leading it to fall in a capillary glass tube. How high the liquid rises or how low it falls depends on the surface tension, capital T, of the liquid. The angle of contact theta formed between the liquid and the tube. The inner radius of the capillary tube, the density of the liquid, and acceleration due to gravity. So the formula is H, or the height or the pressure, is just equal to twice the surface tension multiplied by the cosine of the contact angle theta all over the product of the inner radius of the tube the density of the liquid, and acceleration due to gravity. In using this formula, it is always advisable to express them in the SI units. In question number 1, the height small letter h of the water in the tube is given as 8.4 centimeters. The surface tension, capital T, of pure water at 25 degrees Celsius is also given as 0.072 kilogram per second squared. The density of pure water is equal to 1.0 times 10 to the third kilogram per meter cube. And the contact angle theta is 0 degrees. Our target variable is the inner diameter denoted by capital D, which in fact is twice the inner radius of the capillary tube. And based on the height formula, all right, we will isolate and come up with the working formula for the radius small r, right? That is, the inner radius of the capillary tube small r is just equal to twice the surface tension of water multiplied by the cosine of the contact angle, right, theta, and then divide this by the product of the height of the water inside the capillary tube times the density of water and acceleration due to gravity. So plugging in the given data, we have small r equals 2 times 0.072 kilogram per second squared, okay, multiplied by cosine 0. And cosine 0, as everybody knows, is equal to 1. Alright, so that's understood to be 1. It's not written here anymore. Then we divide by the product of the height of water inside the tube, that is 8.4 times 10 to the negative 2 meters, right? And the density of water, which is 1,000 or 10 to the third kilogram per meter cube, and of course acceleration due to gravity, 9.8 meters per second squared. So doing our math and unit cancellation, we find the radius small r equal to 1.75 times 10 to the negative 4 meters. Therefore, the inner diameter of the glass tube is equal to capital D, which is 0.35 millimeters. So that's the answer to question number 1. For question number 2, these are the given data. We have the surface tension of pure liquid mercury, capital T, equal to 0.458 kilogram per second squared. We're also given the density of pure mercury, equal to 1.36 raised to the fourth power kilogram per meter cube, and the contact angle theta is 135 degrees. the inner radius of the capillary tube, small r, is also given 0.315 millimeters. And our target variable is the depression, small h. So in finding the depression h, we just use the formula for height, which is twice the surface tension capital T and the cosine of the contact angle theta to be divided by the inner radius times the density of the liquid mercury and acceleration due to gravity. So when you substitute the given theta, small h is equal to 2 times 0.458 kilogram per second squared. All right? And the cosine of the angle 135 degrees is negative 0.707 in 3 significant figures. All right? So this product will be divided by the product of R, which is 3.15 raised to the negative 4 power meter, all right, multiplied by the density of mercury, 1.36 raised to the 4th power kilogram per meter cube, and the value of G, 9.8 meters per second squared. So finally, doing your math and the unit cancellation, we will arrive at the value of H, that is equal to negative 0.015 meters. All right? Which when converted to centimeters, that's just equal to negative 1.5 centimeters. It is negative because the mercury inside the glass tube has dropped below the reference mercury level outside the glass tube. That's why we call it the depression of the liquid mercury inside the capillary tube. So that's it. We are done. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.